correspond to the electric field. Okay. So what are the white circles on here? What might they represent in the context of what we just talked about? They are equipotential lines. Okay. What does that mean? Equipotential. The lines connect places which are at the same electric potential. Okay? So we learned a moment ago what the potential as a function of distance, r away from a point charges. It goes as 1 over r. And so these white lines are equipotentials, and of course they are concentric circles. So no big surprise here. But let's think a little bit more about these equipotentials. The potential is the same everywhere, so I can move charges around on equipotentials, and I do no work. That's somehow embedded in the equation that was up here when I defined the electron volt. If I move charges around on an equipotential, they do no work. Even more, because it's a conservative force, I can move charges around, and if I start off with one particular potential point, go on some random walk, and I come back to a point that's at the same potential, I do no work overall. Okay? So these are ideas that I wanted to start sort of absorbing and thinking about. So that one's pretty straightforward. Let's see if I can find more interesting ones. Double charge. Okay, so superposition ideas, again, the green/white arrows, electric field. The white circles, not circles anymore, white sort of ovally shaped things are equipotentials. This is two positive charges. Let's see, dipole charge, equipotentials in white. So I'm going to send out this URL so you guys can play around with it, just to build up some intuition. Let me switch briefly to a 3D version. So now is a 3D version. We've got a point charge. Wow, you're easily pleased. And I don't know, whatever sign the point charge is, the smaller other point charges in a cloud apparently are of the opposite sign. So you see the effect of the attractive force. Let's see. I don't know that I want to show this equipotentials. Oh, not good.
This is broke.
Okay. Try something else there.
Your physics machine broke.
What does this look like? Ah, interesting. Kind of useful, a little bit, kind of two-dimensional. Similar thing, right? I have a point charge, which is, now this is showing, in fact, the electric potential. The white lines are still equipotential surfaces. You can see that the little dots are charges of opposite sign. They're being attracted into the potential well, as it is often called, associated with the point charge of the origin. So you can see the equipotentials, you can see the increasing force, the increasing acceleration, this sort of thing. Interesting. It says charge line. I don't quite know what that means. It's kind of the same. So let's see, what else can I throw on here? Let's look at a dipole. Okay, so I'm going to let you guys play around with this, but to me it's a nice way of building up intuition from equations. And you start to get a feel of the forces and energies and equipotentials. Okay, so let's. Okay, let's see.
It's I see.
Where are we? So we're at all of that. That's good. Equipotentials. We have about 7 or 8 minutes. Okay. So, what might this be useful for? We are working now with a quantity that's a scalar as opposed to a vector. So it's something that simply is magnitude, plus or minus, but the electric potential is a scalar quantity. with electric fields, when we were trying to do electric field calculations, you saw pretty early on that we ran into difficulties associated with, let's say, continuous charge distributions, in that we could only easily access doing the summations or the integrals when those shapes had certain symmetries that made the integrations relatively simple. If you think about that, the reason for it being that otherwise, without symmetries, we've got this change in direction in terms of the small components that each element of charge adds to the complete distribution. And that's where the problem arises. If we're dealing with a scalar, of course, that directional difficulty disappears. And that's one reason why working with electric potential can be helpful. And so, though I don't have time to jump into it today, and I'm going to try and go a little bit faster on this, we can use the same techniques of integration that we invoked for electric fields, but we can use them now perhaps more generally for looking at figuring out the electric potentials rather than the electric fields for more generic charge distributions. Now, that's only useful if we have an easy way to go between the electric field and electric potential and vice versa. Because very often I'm still interested in the electric field. So that's only going to help us if I have some relatively simple way of going back and forth between E and V. Okay? So, let me quickly try and do one of those two directional calculations. The other one we'll do next time. I want you to be reading ahead in terms of techniques for doing integrations of electric potential, using the same ideas we've had for electric field. And then we'll pick up on that next Tuesday. So I'm going to write this as calculating delta V or possibly V from E. And then next time we'll do the inverse operation, though you guys know basic calculus and know how it works, even without us kind of really deriving it. So bear with me. I'm going to run 2 or 3 minutes over time, but hopefully not more than that. And if you're willing to stick around, we can do the famous hair on end demonstration with the Van de Graaff generator and equipotentials. So here's some electric field. I'm going to take a charge, and I'm going to move it along some random trajectory from point 1 to point 2, and I'm taking a charge plus Q0. Okay? So electric field, whatever it is, the path is whatever it is. I want to calculate delta V for this object as it moves along that path. Okay? So what I'm going to do is find out how much work is done. So I'm going to say a small amount of work done along some path element. This is our original definition of work, F dot ds, for a small path length element. In this case, it is Q0E dot ds. I erase this, but you know those two things are comparable. So therefore, the total work done is just the integral of this between starting and end points. That. I can bring Q out front if I wish. Now I need to get the potential difference, which is just the negative of the work done divided by Q0. So this just becomes half integral of E dot ds from 1 to 2. So it couldn't really be simpler, right? Now I've got the way of determining the change in potential. Some random trajectories through some random electric fields. I just need to evaluate this path integral, and that's going to tell me the electric potential difference. Okay. So it tells us that delta V is integral of E dot ds. I said you all guys know calculus. You do. If I was to give you not E, where you're finding delta V, but the other way around, if I gave you V and I asked you to find E, how might we turn this around to get the inverse relationship? So let me just, I can set this as absolute if you like, if I set one of these to be 0. Let me just get rid of the delta for a moment. If I can say that I can figure out V as being the integral of E dot ds, how can I flip this around and find E if I know V? Sure. So we'll talk a little bit more about this formally next time. But you can imagine now that E is minus, and look what I'm doing here, and you guys all know enough calculus for this to make sense. It's now the partial derivative of this scalar quantity with respect to a certain direction, okay? So think about what this is doing. It's giving me the electric field along that direction. And so in principle, if I need to figure out the total electric field, I better know what this is in several components, of course 3 components if we're talking about a 3-dimensional space. So this allows me in principle to go back and forth between electric field and electric potential. All right, so didn't get quite as far as I wanted to, but just to wrap things up on an entertaining note. I don't know why I'm doing this, it's not really relevant, but does anyone want to do the hair on end? Come on down. The only reason to do this has to do with possible, very peripheral demonstration of equipotentials. Okay, hold that. I want you to turn towards this and both
Yeah, it's too heavy, so I don't know. Oh, you gotta get about. It's not bad. It's not bad.
a little bit away. Okay. So,
Dang, that's really good.
of course, the charge is getting built up all over.
Oh my god.
And charge, wow, this is a really good one. The charge likes to get as far away from its neighbors as possible. And when you have something that's able to move freely, like long hair, if you think about it, the way to do that is to go radially outwards. So this is actually awesome.
It's like seeing them
The
in
best person I've ever seen do this. What you can imagine is there's a buildup of charge. Your head is a little bit like a point charge. And so there are electric field lines radiating outwards. And you can imagine having concentric spherical equipotential surfaces around the head here. Okay? So that's the only reason I did this, so I could illustrate something about equipotential surfaces. So don't let go. I'm just going to discharge this. Okay, you're good. Just say. All right. Two things before you leave. Feedback, just place it on the table at the front.
Really good.
Free lunch. Does anyone think you have better
If there's anything I can do in this class, I can my hair stand on one end.
Man, I had my hair changed about that.
We were like, oh, your hair's too long. It's not gonna work. No, dude, we were so wrong.
It's in middle school, this is the only thing I can do.
So you just like you do it, and then when you watch it, you shock each other.
Yeah, no, like, we had the same thing in our school and not have no changing. What? You got this wrong. Sorry? No.
Oh, I don't know either. I just, like, he has all the things I just not using. Oh my god.
Oh, wait, why did you guys sit so far away?
I pulled it that last time.
Storage is good though.
Oh, good job. Now to just hide my hair. Oh, I should just stay up there and see. Oh, damn. You know what? I'll just do it later. That's like 2 things, right?
I don't want to go. Your friend who's really you lost his life instead of one. Okay, other quick questions. I got to evacuate this from the building.
Happens to an ostrich when it
No, that's a great question.
does it actually get ignored? Because I wish, like, you know, in terms of this company, but it'll come back and bite us.
Good news is,
Let's see, anything down that end? A quick question. Not too bad. Probably just gonna do that outside. Right back. That's what we do. Nathan, if, I don't think I'm going to make it today, but if you still have questions tomorrow,